Hello everybody and welcome to the latest edition of the Physics Corner, a video series in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we are working on conservation of linear momentum, specifically for what we call elastic collisions. So, a couple things going in. Because it's a conservation problem, it's very useful for us to draw or to envision the situation before and after. So here we have a picture of two carts before they collide, and here is a picture with some question marks, of course, after they collide. The reason for doing this is because that's how the conservation principles are applied in physics. What we want to understand is how much of a certain conserved principle or quantity is present immediately before and immediately after the situation or the event in the problem. So in case of momentum, in this case linear momentum specifically, that event is a collision. So in short, a collision can be thought of as a really important or very quick change of the individual momenta or velocities of objects involved. Okay, so now that doesn't mean, by the way, they necessarily have to touch. You may have situations like we're describing here today in your lab, where you'll have, say, magnets on opposite ends of your carts that you'll be playing with, and if you push them slowly towards each other, because of the magnetic fields, the carts might not ever actually physically touch each other. But we still call that a collision in physics. So collision doesn't necessarily mean that the objects physically touch each other. It doesn't mean they undergo kind of a radical change of their motions. Okay, so in any case, that's what we're talking about today is elastic collisions. Now, elastic collisions have two properties or two conditions. One is that the linear momentum itself is conserved. Now, that particular property is true for all momentum conservation problems, but the other property, which is additional for elastic collisions compared to other types, is that the kinetic energy also remains the same before and after. And again, it's always for the system, not for individuals. Individual momenta, individual kinetic energies, individual velocities, all of those things are open to change. It is the before and after of the system, the objects together, that matters. And that's what we have to pay attention to here. So here's our question. In a particular lab experiment, you can envision doing this perhaps. You have a small cart on a track and you push cart A along the track and it's headed towards cart B. Cart B is stationary. Cart A will give an initial velocity of 1 meter per second. Now I have to be very careful about saying this. More specifically, the velocity of cart A will be 1 meter per second immediately, the instant before the collision. If you've ever played with actual carts on actual tracks, there's usually a little bit of friction between the cart wheels and the track, and so the cart might actually slow down a little bit from the moment between you when you're pushing it and when it actually hits the other cart. We're not worried about that. We're worried about the speed of the incoming cart immediately, the instant before the collision happens. So that's what we're talking about here. So when I say this, that's why I say it that way. Then we're also asking the question, what happens the instant immediately after the collision, after the two carts separate? Okay, and that, by the way, is the point. Elastic collisions, again, are where the objects will separate from each other. So that's another way to think of it. Now, the reason we have to be careful in our description of the conditions is because it is possible to have two objects collide, separate, but not to be a completely or ideally elastic collision. There might be some differences of kinetic energy present. We are going to assume it is an ideal elastic collision where the kinetic energies, the totals, are the same before and after. Okay. We'll perhaps do a video where we'll learn how to handle that more complicated situation, but that's for another day. Okay, second thing is, in this particular video today, we're only going to focus on this special case of the carts having exactly the same mass. That turns out to be important, as we'll see as we go along with the algebra that we're going to perform today, to know the relationships between the masses, or at least that's a very useful thing to know. The algebra can get very complicated, very hairy, very quickly, if you don't have some known relationship between the masses of the two objects involved. And like we always like to do, let's tackle the simplest possible cases first. Once we know how to do the simpler cases, then we can worry about more complicated ones. So the simplest possible way to do this is to assume that the masses of the carts are identical. In a future video, we'll talk about how to handle the situation if the carts are not the same mass. But today, in this video, same mass. So, let's go ahead and get started. That means the mass of cart A equals the mass of cart B, all right? Now, I could go ahead and give you a number. I could say, oh, each cart has a mass of 1 kilogram or something like that, right? I'm not going to do that, and you'll see why I will not do that part in a moment, but we'll say that. Okay, and the initial velocity, or the velocity of cart A immediately before the collision, is 1 meter per second. I'm going to call that AO, VAO, velocity of cart A originally, if you will, be 1 meter per second. And you'll see why I need to use all these subscripts coming up in just a moment. Okay, what are the unknowns? Well, the masses are already related to each other. What we're interested in finding out in this particular problem is the velocities of the carts after. Now, the velocity of cart B before the collision will be 0, so let's make that official. So VBO, if you will. But VAF, the velocity of cart A after the collision, or the final velocity of cart A, and VBF, the final velocity of cart B, those two velocities will be unknowns. We need to find those out. All right, so let's start there. Okay, now the conditions for an elastic collision are these. So let's write them down so they're explicitly in front of us today. First off, momentum is conserved for the system. So when we write out something like this kind of statement, that's what we mean. It's not the momenta of an individual cart. That obviously can change. It's momentum of the system that we care about. And because elastic collision, the kinetic energy of the system, again, have to keep emphasizing the system, not just individuals, but the total of the system will be conserved before and after. Okay, so that's our setup. Let's go ahead and apply our conditions. All right. So this is how we get started on this kind of problem, by the way, is that we have to know the conditions. What do we have available? What kind of collision is it, for example? And that tells us what equations we can apply. Also remember, as usual, these particular equations are general equations, right? They're general statements. We have to adapt these to our specific problem. So let's do that. So first equation is momentum conservation. By the way, you don't have to do these in this order, but you have to do both eventually. So momentum going in. Cart B is standing still to start with, so there's no momentum of cart B at the beginning. But cart A has momentum as a mass times a velocity. And oh, by the way, we should probably write that down off to the side to remind ourselves what momentum is individually. So momentum of cart A is then mass of cart A multiplied by velocity of cart A originally, like that. Okay? How about the momentum after the collision happens? Well, we don't know going in. Now, by the way, you might already suspect what the answers are. You might have already gone through a problem like this and know what the answers are for that matter, but we're going to assume we don't. And I want to show this off so we can see how the math plays out for us and gives us what we expect to happen. So we're going to assume that cart A has a velocity afterwards, so we'll call that VAF, and therefore the momentum of cart A after the collision is MA VAF, like that. Then there's the momentum of cart B after the collision, so mass of cart B and VBF, like this. So that equation looks like this. Now, here's something we can do to shorten this up right away. We already said, this is important for us today, that these masses are the same. So mass A, and mass B, which is also mass A, they're all the same. So those all can be canceled or removed, and we're left with an equation that just looks like this. VAO equals VAF plus VBF. So one equation right there. We'll star next to it to indicate that that's important for us to look at. Okay, that's our momentum equation, but one equation, two unknowns, at least officially. Again, we might suspect some of the answers, but let's do this officially. And so I need a second equation with these unknowns to be able to solve this system of equations, right? So that's the kinetic energy part. So kinetic energy in equals kinetic energy out, or immediately before and immediately after the collision. That'll be 1/2 MA VAO squared. Oh, and again, just to remind everybody where I'm coming up with this, right? Kinetic energy in general, 1/2 mv squared. So here it is applied to the specific cart. Again, for this case, cart B is not moving to start with, right? So no kinetic energy for cart B to begin. After the collision happens, it's 1/2 MA VAF squared plus a 1/2 MB VBF squared, like this. Okay. Same logic applies. Notice that 1/2 is common to all three terms. So get rid of the 1/2. And again, mass of cart B is the same as mass of cart A. So we can again eliminate those. And this simplifies to this statement. VAO squared equals VAF squared plus VBF squared, like that. And that's our second equation. Okay. So we now have two equations, two unknowns. That means we can do a solution, right? We can do some algebra to solve for this. There's a couple of different ways to go about this. I'm going to choose one particular way. You can follow me along. If you know some other ways or some other versions of doing this that you prefer to try, by all means, I'll show you one of mine and talk about it. Again, we don't know what either of these two terms are, so we have to solve for those. VAO is 1. Now, you could, at this stage, if you wanted to, just plug in the number 1 in both of these spots. I'm not going to yet. We'll put that in place when we need it. But you could if you wanted to, if you think that might help you simplify it or make it easier to see the solution. Okay. All right. Second thing is, something to be very cautious about at this stage. We have these two equations here and here, and it looks like all you need to do is take this equation here to get these things to match, is just take each of these three terms and square it. And then, then you got this equation. Let's be very careful with our algebra. Okay, so let me show you what I mean. So what I would like to do, or what I need to do, is choose one of these unknowns, solve for it here, and then substitute that somehow over here. All right? Let's take a look. So let me go ahead. I'll solve in this particular case for VAF. Right? So if I take this equation here, VAF will equal VAO minus VBF, like that. Right? So I'm just moving VBF to the side. Now, if I want to substitute this into here, I just need to square this, right? So that is VAF squared. So get this, square it, and I'm going to find out what's on this side and substitute here. But be very cautious. VAF squared is not VAO squared minus VBF squared. It's not that. Remember our algebra. Let's go ahead and I'll illustrate it by drawing this out a little bit. This should be an O here. When I square this, what I'm really doing is this kind of trick, right? So this will help us understand why we're going to get what we get and why we have to be careful with our algebra. So VAO times VAO gives us a VAO squared term. VAO multiplied by a negative VBF gives us a negative VAO VBF. This term is a VAO multiplied by another negative VBF, which means there's two of them, right? And then VBF multiplied by VBF, the negatives cancel, and I get a plus VBF squared there. So when you substitute, you have to take the long way around. You can't shortcut at this stage. If you try to shortcut, you're going to get messed up. So let's not shortcut. Let's do this properly. So what I want to do then is for this equation, substitute for this fellow here with this stuff. So let's do that. I'll get started here and we'll continue. So VAO squared equals, what's VAF squared? VF squared is really this stuff now. So VAO squared minus 2 VAO VBF plus a VBF squared. So that's this stuff right here is all of this. Now, don't forget, there's also a plus VBF squared here as well. Like that. So don't forget that extra term. Just because you've got a VBF squared here doesn't mean you can forget that one. They come from two different sources, right? So let's now do some more algebra. So to let everybody see what we're doing, let me recopy this very quickly. So VAO squared equals a VAO squared plus, or excuse me, minus, sorry, VAO to VAO, VBF, plus a VBF squared, and plus another VBF squared. So that's what I left off with just a moment ago. All right, let's consolidate. So if we look at this equation as written here, VAO squared equals, oh, there's a VAO squared. I can subtract VAO squared from both sides, and that eliminates this. That goes away. Which means, by the way, this side is equal to 0. That's okay. Don't worry about it. Something else. VBF squared plus another VBF squared gives me 2 of them. So 2 VBF squareds, like that. I have a minus 2 VAO VBF. Like that. So all of these are on one side and then 0 on the other side, like that. Okay. I can do a little bit of consolidating here. Notice the number 2 is common to both of those. Get rid of it. Let me write it down so we can see exactly what's happening and why. And now at this stage, let's go ahead and filter a little bit. There's 1, not 2, but 1 VBF term common to both terms. So let's pull that out. And if I do that, I have another VBF here, right? So VBF times VBF gives me VBF squared, right? Then if I pull the VBF off of this one, I'm just left with the VAO here. And this is my solution. Okay, solution for what? What did I get? What has happened? I actually have 2 possible solutions, okay? Now, sometimes in math you always get you get 2 possible solutions this way. Sometimes in physics, one of the solutions is meaningless or doesn't matter. Sometimes they do both matter. In this case, they do both matter if we think about it carefully. So either we have this, either VBF equals 0 or VBF minus VAO equals 0. Okay, what does this mean? VBF equals 0. Okay, that's telling us the final speed of cart B. Well, we know the final speed of cart B isn't 0 for real, but what does it mean physically? It means, oh, well, before the problem started, before the collision, the velocity of cart B was 0. So this is actually just recovering the fact that cart B was 0 before the collision. That's actually what that means. What about this one over here? This one is what we're really interested in. The final velocity of cart B is equal to the original velocity of cart A, which, by the way, was our 1 meter per second if we want to go back to the numbers. Notice, by the way, I didn't have to put the numbers in until the very end. I could have put it in again long ago, but actually in this particular case, it was a little more instructive, and it actually worked a little more smoothly to wait until the end to put the number in. Okay. But, so, what does that mean? Let's go back to our picture of our carts. What it means is this. Cart A comes in, hits cart B. Cart B now has the same velocity as cart A did immediately before the collision. That's what that means. All right. So, in other words, cart A comes in and gives its velocity to cart B, if you want to think of it that way. All right. What about cart A, the incoming cart, after the collision? What happens there? Well, a couple things. We can go back to our solution here. Let's take a look. Here's our equation that we solved for. We did this on purpose, remember, right? We solved for the final velocity of cart A, and we found out it's this. Let's rewrite that down. So VAF was equal to VAO minus VBF, like that. Okay. Again, that's the step we took to do this algebraic solution, right? But these two are the same. We just said so, right? Check it out. If these two are the same, then subtracting them gives us 0. So what does this mean? Cart A comes to a dead stop. So let's think about this. Again, come back to our picture here quickly. This isn't moving. So this cart comes in, hits cart B. Cart B takes off with the same velocity that cart A used to have, and cart A stops, just like cart B used to do. They trade, if you will. They do an exact perfect swap of velocities. The cart coming in gives, if you will, its velocity and energy and everything to cart B. Cart B takes away all the energy and velocity and momentum of cart A. They exactly trade positions. Okay, and the mathematics goes ahead and shows us that. So, now again, you can see this very clearly in an experiment if you try it. It happens right in front of you, so it's easy to see. But this is the algebra and the physics explaining why it works the way it works. Okay. Now, that is usually not the case, that both the carts have the same exact mass, or two objects in general have the same mass. How is that going to work? That's a future video, everybody. All right. Technical support for this program is from Sidney Gouchow and Sophia Turner. Funding comes from the University of Mississippi and the University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi. I am your host, Dr. Christopher Sorolla, thanking you for your attention, and clear skies.